Hello, I'm Sebastian. Welcome to 9 Trees podcast. Today, I will summarize and review the book. Quantum Mechanics, The Theoretical Minimum by Leonard Susskind aims to take readers from curiosity to working competence in the core ideas of quantum theory, without the heavy formalism or encyclopedic scope of a full university textbook. Built around the philosophy of learning only what is essential to calculate and reason, it introduces the mathematical tools and conceptual shifts that distinguish quantum mechanics from classical physics. Susskind, known for clear, rigorous teaching, emphasizes how quantum theory encodes physical predictions through states, operators, and probabilities rather than definite trajectories. The book is designed for motivated beginners who can handle algebra and basic calculus, and it rewards readers who are willing to practice. Rather than leaning on mystique, it treats quantum mechanics as a precise framework with well-defined rules and testable consequences. The result is an accessible path into a famously challenging subject, useful both for self-study and as a structured complement to more comprehensive courses. I will give you key takeaways from this book. Firstly, from classical intuition to quantum rules, a central topic is the transition from classical thinking to the rule-based logic of quantum mechanics. Instead of describing a particle by a definite position and momentum evolving along a trajectory, the quantum framework starts with a state that contains all accessible information and evolves according to specific mathematical laws. The book emphasizes that quantum mechanics is not a collection of paradoxes, but a compact set of principles that can be learned and applied. Readers are guided to accept that probability is fundamental, not merely a sign of ignorance, and that measurements play a special role by connecting mathematical states to observed outcomes. This topic also clarifies what quantum theory tries to predict, not what happens in a single run, but the probabilities of various results across repeated experiments. By drawing careful contrast with classical mechanics, the text sets expectations for what must be unlearned, such as the assumption that every property has a definite value at all times. This foundation prepares the reader to treat later chapters as a coherent system rather than isolated tricks, and it frames quantum mechanics as a practical language for calculations. Secondly, state vectors, superposition, and probability. Another major topic is the idea that physical states can be represented as vectors in a mathematical space, enabling superposition. Instead of a system being in one configuration or another, it can exist in combinations that only become definite when a measurement is made. The book develops the meaning of amplitudes and how they relate to measurable probabilities, highlighting the difference between adding probabilities and adding amplitudes. This distinction is where interference enters, explaining why quantum outcomes can deviate sharply from classical expectations. The treatment builds intuition for how to read a state as a catalog of potential measurement results, each with an associated likelihood derived from the state. It also introduces normalization and the need for consistent probability assignments, stressing that the formalism is designed to preserve total probability. This topic supports practical computation, such as predicting outcomes for different measurement choices, and it frames quantum weirdness as the natural consequence of vector addition and projection rather than as philosophical fog. By repeatedly connecting the math to experiments like two-path interference, the book helps readers see superposition as a working tool. Thirdly, observables, operators, and measurement outcomes. The book treats measurable quantities as observables represented by operators acting on states. This topic develops how measurement corresponds to selecting a basis tied to the observable and how possible outcomes align with special states associated with that operator. The explanation links eigenvalues to measurement results and eigenstates to the states that produce a definite outcome, while also showing what it means to measure an observable when the system is not already in an eigenstate. The framework naturally yields probabilities for each outcome and describes how the post-measurement state relates to the observed result. This is also where non-commuting observables become meaningful. The order of measurements can matter because the associated operators do not generally commute. The consequence is not just conceptual, but computational, affecting which properties can be simultaneously sharp. The book uses this operator language to replace vague discussion with a precise recipe, pick the observable, express the state in the corresponding basis, compute probabilities, and update the state accordingly. Readers gain a structured way to analyze measurement scenarios, which is essential for understanding uncertainty, compatible observables, and the logic behind many standard quantum experiments. Fourthly, time evolution and the Schrödinger framework. A key topic is how quantum states change in time. Rather than evolving by Newtonian forces applied to coordinates, the quantum state evolves through an equation driven by the system Hamiltonian, the operator that represents energy and generates time translation. The book focuses on the practical meaning of this statement. Once you know the Hamiltonian and the initial state, you can, in principle, predict the state at later times, and therefore the probabilities for future measurements. The discussion connects unitary evolution to the conservation of total probability and emphasizes that quantum dynamics is deterministic at the level of the state, even though measurement outcomes are probabilistic. This topic also clarifies the distinction between evolving the state and updating it due to measurement, two processes that obey different rules and can be confused in popular accounts. Through examples such as simple two-state systems and basic potentials, the reader learns how energy eigenstates simplify time dependence and how superpositions lead to oscillations and interference in time. Overall, this section supplies the engine of prediction in quantum theory and shows how the abstract formalism becomes a calculational machine. Lastly, spin, two-state systems, and entanglement intuition. The book uses spin and other two-state systems as a compact laboratory for quantum reasoning. Because the mathematics is manageable, readers can see superposition, measurement, and dynamics at work without the technical overhead of continuous variables. Spin highlights how quantum properties can be intrinsically discrete and how different measurement directions correspond to different bases. This naturally leads to a clear illustration of incompatible measurements and the limits of classical hidden variable intuition. Building from single systems, the text motivates the idea of multi-part states where the combined system has more structure than its components. Here, the notion of entanglement becomes intuitive. The state of the whole may not decompose into independent states for each part, producing correlations that cannot be explained by shared classical randomness. The emphasis remains on operational predictions, namely how to compute joint probabilities for measurement outcomes on separated subsystems. By focusing on simple but deep examples, this topic equips readers to understand why quantum information concepts matter and why entanglement is not a philosophical add-on but a direct consequence of the state vector framework applied to composite systems. In conclusion, this book suits readers who want a serious introduction to quantum mechanics without enrolling in a full semester course. It is ideal for engineers, software professionals, scientifically minded general readers, and students preparing for physics study, provided they are willing to do some math and practice problems. The benefit is practical literacy. You learn the minimal set of concepts needed to compute predictions and to interpret common claims about quantum phenomena with more precision. That competence can enrich your life by sharpening analytical thinking, improving comfort with abstract models, and giving you a clearer view of technologies and research areas influenced by quantum theory, from semiconductors to quantum computing discourse. It is worth buying compared to many popular science treatments because it prioritizes the working framework over storytelling or mystery, while still avoiding the intimidating breadth of standard textbooks. The emphasis on states, operators, measurement, and time evolution gives you a transferable toolkit rather than isolated facts. For readers who have tried softer introductions and still feel unsure what quantum mechanics actually says, this provides a structured bridge to deeper study and more advanced resources. If you would like to support Leonard Susskind, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.